Hello, my name is Nikhil. Today my group and I are going to give a presentation entitled The Exploration of Photons. So throughout the ages, many of the world's great minds have asked the question, what is light? So while some had great insights into the behavior of light, others didn't quite. And eventually, as time progressed, things were worked out. The 17th century brought in a great wave of new thinking, and our classical wave description of light was formulated. You all should be familiar with waves, with the frequency being 1 over the oscillation time, and the wavelength as being the separation between the crests of the wave. The visible light we see all around us forms a very narrow part of the full light spectrum. We see the purples as being a higher frequency, lower wavelength part, and the reds being the longer wavelength, lower frequency parts of the light spectrum. On the extremes, we have radio waves with huge wavelengths, and on the other side, we have X-rays and gamma rays with very, very narrow wavelengths. The classical wave description of light could not account for all of the behavior of light that we saw. For example, things like the photoelectric effects could not be explained. This remained a problem until Einstein came along in 1905 and gave us his wave-particle description of light. Rather than imagining light as a classical wave, Einstein described light as actually composed of packets of energy with specific amounts of energy, and their motion was wave-like. We call these packets photons, and the key point is that the energy of the photons is proportional to the frequency of the light. Higher energy photons correspond to higher frequency light. If we have a photon with very low energy coming towards an atom, the photon will simply pass through the atom if it does not have enough energy. If it has slightly more energy, it can promote an electron to a higher energy level. The electron will sit there for a while and eventually go back to its ground state, emitting another photon. If a photon comes in with a high enough energy to promote the electron past each of these energy differences, the photon will be absorbed and the electron will be liberated. I'll now pass it to Mireille, who will talk to us about Xray Generation.
Hello, I am Mireille. So my work is to probe electron beam when traveling through solid target. So first, we are generating free electron by the interaction between high intense laser pulse, typically 1 petawatt laser pulse with solid target, and when the petawatt interact with the solid target, we manage to generate free electron, and those electrons travel through the target close to the speed of the light. So my job is to characterize the electron beam when he is traveling through the solid target. So as we can't probe it directly, we are using lateral way to probe it. Here you can see an example of how we can characterize the electron temperature and also the diversion and the spatial distribution of the beam by observing the X-ray generated when those electrons interact with atoms when they are traveling through solid targets. And why we are doing that for fast ignition. And also we can imagine improving X-ray sources.
Hello, my name is Jonathan and I'm going to be speaking about fluorescence. We've already heard about light as photons, excitation of electrons and emission of electrons from samples, and these are the main ideas I'm going to be following up as we look at fluorescence. Hopefully give you a brief idea of how it works, what it is, how it's useful for physics, and at least one area in which it'll be useful in the future. So, you may have heard about fluorescence. I've certainly used the word a few times already, but you may not know what that is. Whether that's the case or not, you've definitely seen it. Here, for example, is our standard chemistry lab fluorescent chemicals in beakers that you've probably all seen somewhere. In nature too, we have fluorescence, such as these green glowing corals. The same principles as take place in fluorescence are what is used for glow-in-the-dark objects, such as children's toys, and an example of that is this fellow here. One of the more interesting examples in the world of fluorescence is these genetically engineered Taiwanese pigs who in fact do glow bright green when shone upon with ultraviolet light, and I just think they're very interesting indeed. So what is fluorescence? I've been whittling on about it, but how does it work? As Nikhil has already told us, sometimes molecules can absorb photons of light. So a photon comes in, excites an electron, and in the fluorescence phenomenon there's a slight delay, a nanosecond or 0.000 many 0.1 seconds delay. And when this photon is emitted again, it's of a different wavelength, so a different colour of light comes out. This is most obvious to us when invisible light is absorbed and invisible light emitted. And you'll have seen this in bowling alleys, laser quest, and dancing, when ultraviolet light is absorbed and we see visible fluorescence, such as these black light shone upon trainers. It's all very interesting and it gives nice pictures, but is it useful in the lab? Well, yes, is the answer. We can use this to get very sensitive information about samples. This rough schematic that we have here shows you shine light in, you collect the fluorescent data, and from this information, from the wavelength change, from the time it takes for the light to get emitted, we can get a very sensitive, very accurate idea of what we have in the sample. Not everything fluoresces, however, so if we want to look at some more complex systems, we may have to make them fluoresce. We can do this by attaching molecules onto them. So this here is a fluorescent molecule. It's just a molecule, don't get scared by it. But we can attach that onto biological samples, such as seen in this artist's representation of a DNA strand with the fluorescent probe attached. And with these probes attached to biological molecules, we can get good information on the sample environment, on structural changes to the protein, and real-time information on structural changes and what's happening with the samples. This information is of course very useful for biochemists, for biologists, and it's a good example of different scientific disciplines working together and using the same technology. So we can attach this to DNA, we can also do it with other less complex molecules, and my PhD shall be looking at finding ways to get fluorescence information on glucose molecules. Now, glucose doesn't directly fluoresce, but there are ways around that, and that's the work that I'll be doing over the next 3 years to look at this. Why glucose? Well, diabetics, they have to test their blood every few hours in order to get good control, and they're testing for glucose. The way they do this, as you can see in the top picture, is just by cutting open their finger and taking a blood sample. If we can get the fluorescence techniques perfected, then we could, in theory, shine a light onto the skin, through the skin, and get the fluorescence data at the other end, and therefore diagnose what's happening in the blood without cutting open the patient. So this non-invasive analysis would of course be very useful for diabetics, for diagnostic treatment, and it would overcome many of the problems currently associated with the technique. So hopefully one day we can go from the top picture of cutting ourselves open to the bottom picture of shining lights on people to find out what's wrong with them. There are other ways that you can get light out of samples, not just fluorescence, and now Simon's going to come and speak to us about emission of light from solid state sources.
Hello, I'm Simon, and I will be talking about solid state physics, in particular optoelectronic devices and solid state lighting. So I will now try to convince you that solids can emit light even without high energy lasers, as you have seen in Mireille's talk. And semiconductors as a subclass of solids are used to create LEDs. You will all have heard about LEDs. That's light-emitting diodes, and you can find them almost anywhere. For example, in car lights, in just different color LEDs. In the reverse project, you can actually make solar cells out of it in huge displays. And you will ask yourself, how is this being done? Well, you've all heard about the basic physical principles behind it in the earlier section of the talk. And in a solid, it's slightly different. Because the specific composition and configuration of atoms change the energy levels where the electron can fall down, and therefore a specific band gap is there, and this relates to the color of the emitted light. Therefore, a specific light color is inherent to a specific composition and configuration of atoms. Right. Now I would like to talk about a very special group of semiconductors, that is the group 3 nitrides, and that is the semiconductor group I'm talking about. I'm researching in my PhD, sorry. If you look at the third group in the periodic table, and you all know about the periodic table, then you can combine gallium and indium with nitrogen to form a semiconductor emitting in blue. This blue emitting light, the semiconductor has a very high internal quantum efficiency of more than 90%, which is very good, and this is actually being used, for example, to create white light with the help of fluorescence. Now, you've all heard about fluorescence. The blue LED can be coated with a yellow fluorescent, and in combination with a transmitted blue light and the yellow light, white light is being created. So this is probably what you've seen almost anywhere. If you see it, street lighting, for example, you have this bluish kind of color. This is what you see. But the group 3 nitrides actually offer a different path. For example, if you look at the top right corner into the graph, you can see that gallium nitride emits at a certain energy which relates to a color, and this is actually in the ultraviolet. Indium nitride is in the infrared, and in between is the whole solar spectrum. So different compositions, and will allow you to create LEDs with any color. Now, I've already told you that blue is very highly efficient, but the other colors are not. And this is what I'm researching on. And you may ask yourself, why is that so important? Why so much effort in it? Well, the applications, of course. For instance, you can create high-efficiency solar cells. If you can span the whole solar spectrum, you can actually use all the energy in the light that is used to create electricity. And you can, as I've already told you, create high-efficiency LEDs in all colors. This is already used in many applications. You can use it in water purification, biosensing, and high-density data storage. That is your average Blu-ray display, where you have a blue LED emitting using indium gallium nitride, for example. And now Nikhil will summarize.
To summarize, you've now learnt about a particle description of light, how we can use high-intensity lasers to generate fast electrons. You've learnt about fluorescence and how we can use that for a glucose sensory device, and about solid-state lighting sources. Thank you.